Hi, welcome back to the introductory video on acids and bases. This is part 2 of 2. Excuse me. In part 1, we discussed properties of acids and bases and also how you need to recognize them. Key information from part 1 that you absolutely need to know are highlighted in yellow. Everything else is sort of additional information that could possibly be interesting or could help you at some point. But you definitely need to know the stuff that's highlighted. For example, water acids produce H plus, bases produce OH minus when dissolved in water. How to recognize acids and bases from their chemical formula, and that acids have a pH less than 7 and bases have a pH greater than 7. So these are key things when we're talking about acids and bases that you should know about them. We also looked at the pH scale, which again, we said is an indicator for if something is an acid or base. Not only you can tell if something is an acid or base, you can tell which acid is stronger and which base is stronger based on the pH scale. We'll go through later a list of strong acids and strong bases, but just know that for the pH scale, the lower you get, the more acidic, and the higher you get, the more basic. And if you're at a pH of 7, you're neutral. That means you're neither acidic or basic. Finally, we looked at the neutralization reaction, which is what happens when acids and bases get together in a reaction. They undergo a double displacement that produces a salt and a water. So just like how we had to know that combustion reactions produce CO2 and H2O, for example, you have to know that acid and base neutralization results in a salt and a water. So that's something that's super important as well. So those were the key highlights from part 1. Part 2, we're going to talk about conjugate acids and bases. We're just going to briefly touch upon them just so that you're aware of what they are. Then we'll go into some naming rules, which is of this video is the most important part of this video, and then acid and base indicators, which are also important. So let's start off with conjugate acids and bases. We saw the reaction of acids and bases to produce salt and a water. When acids and bases react, the products they produce are their conjugates. So starting with an acid. The conjugate acid is a species produced when a base accepts a hydrogen ion from an acid. And a conjugate base is a species produced when an acid donates a hydrogen ion to a base. So let's take a look at that. The main part of the base is the OH minus part, and the main part of the acid is the H plus part. So for this base, the OH minus or the hydroxide, when it gains a proton, it forms water. So this water is the conjugate acid of that base. On the other hand, for the acid, when it loses that proton, it's left with Cl minus, which is found here in the magnesium chloride. And so the conjugate base of that acid will be the salt. So how do we write an acid? It's a conjugate acid or base. If we're starting with a base like NH2CH3 and we want to write its conjugate acid, what we need to do is we need to cause that base to gain protons. Since that's the definition of a conjugate acid, it's what's the species that's produced from base when it gains a proton. So we're just going to add a proton to its chemical formula, and that's real simple. So if we're adding a proton is an H plus. What we're going to do is we're going to gain a hydrogen, and this is a hydrogen that's attached directly to the nitrogen. So we go from NH2CH3 to NH3CH3. And then we also gained a positive charge, so that will increase by a plus. So when we're forming a conjugate acid, we gain a proton. So notice how we went from NH2 to NH3, and then we also gain a plus charge. On the other hand, when we're trying to write the conjugate base of an acid, so if we're starting with water and water can act as an acid, even though water is neutral, water in the presence of a base will act as an acid. We can remove a proton from water. And when we do that, we would decrease the number of hydrogens, so we go from H2 to OH. And then since we're removing a positive charge, that's the same as saying we're gaining a negative charge, we form OH minus. So we go from a neutral H2O to a negative OH minus. Here's a couple more examples. So again, for conjugate base, remove an H plus, and if we do that for HF, you get F minus. And for NaOH, if you want to form its conjugate acid, you got to gain an H plus, and then for that you would form H2O. So this just give you an idea. Conjugate acids and conjugate bases are what's produced from acids and base. So a conjugate acid is produced from a base, and a conjugate base is produced from an acid. Now, in addition to just like knowing the terminology, conjugate acids are important in real life because they're used in making buffer solutions. And buffer solutions are solutions that maintain a steady pH. And so to make a buffer, you take a base in this conjugate acid, or you can take an acid in its conjugate base. And these would have to be what's known as weak acids and weak bases. We will touch upon that later, so you'll know that there are weak and strong acids as well, and bases. But for right now, just to know that the buffers are made from bases and their conjugate acids, and acids and their conjugate bases. So what's an real life example of a buffer? One real life example is your blood. Your blood maintains a constant pH between about 7.35 and 7.45. Outside of that range, you will die. So how does your blood maintain that pH, considering it's exposed to all sorts of acids and bases that flow in the system? And that's through this buffer here. This buffer involves carbonic acid and its conjugate base, bicarbonate. And so these arrows, which are called equilibrium arrows, are showing that the acid and bases are in constant equilibrium. So if, for example, you add an acid to the if your blood gets too much acid, the equilibrium will shift to form more of this base, which will neutralize the acid. If, on the other hand, your blood has too much base in it, it will shift to form more of this acid to neutralize that. So this is how sort of a buffer works. It sort of works in equilibrium, shifting back and forth until the right pH is maintained. All right, so now here's probably the most crucial part of this video is just naming acids. And it says naming acids and bases, but really we're focusing on naming acids since the bases are metal hydroxides and we already know how to name those types of ionic compounds. So naming acids, we're going to start with binary acids, and that will be something like HCl, which has just two types of atoms. So for binary acids, you start off with the prefix hydro and you use the suffix ic acid. Let's look at an example. HCl. So HCl has hydrogen and chlorine in it. The name of this acid would be hydrochloric acid. So again, we use the prefix hydro, and then the suffix is ic acid. Let's look at another example, H2S. This is also a binary acid because it's made of just two types of atoms, hydrogen and sulfur. And once again, we start with the prefix hydro, and since it's sulfur, it will be sulfuric. So that's hydrosulfuric acid. Okay, so we'll look at the ones with polyatomics in a moment, but I just want to point out to where the binary acids are found. Mostly they're made from nonmetals in group 17, but there's also a couple in group 16 and one in group 15 that make binary acids. And so here are their examples. All right, now let's talk about naming polyatomic ions. So acids made from polyatomic ions. And the rules are different. First of all, there's no prefix, there's no hydro. And the suffix will be determined by the name of the polyatomic. So if your polyatomic ends in ate, ATE, like nitrate, sulfate, phosphate, the corresponding acid name will be ic acid. If, on the other hand, your polyatomic ends in ITE, ite, the suffix of your acid will be us acid. So let's take a look at the example HNO2. First thing we have to do is figure out what's the name of the polyatomic. That's NO2 is the nitrite. So since it's nitrite, the ending of that acid will be us acid. So this will be nitrous acid. If, on the other hand, our polyatomic ends in ate, like in HNO3, so nitrate, we would then use the ending ic acid, so this will be called nitric acid. All right, so the general way we can memorize that is for when your acid comes from a polyatomic, it's ate ic, ite us. That mnemonic is helpful. Here are some more examples, just so you can get a sense of what they sound like. All right, now that you've looked at those examples, let's try this CFU. So pause the video now. When you press play again, the answer will be revealed. Okay, so CFU A, the answer is false. For something like HNO3, we don't use the prefix hydro because it comes from a polyatomic ions. We only use hydro when it's a binary acid, an acid made of two types of atoms. And then for the second one, chlorite, the name of the acid, since it's ends in ite, will be us acid, chlorous acid. All right, here's some practice. There are 8 examples here. You can pause the video, and when you press play again after trying these practice problems of either like writing the name or writing the chemical formula that corresponds to it, after you've done that, plus press play and the answer will be revealed. Here are the answers. Okay, now that we've looked at naming acids, that's something that we'll spend a lot more time practicing on. So if you don't fully get it right now, that's totally fine. In fact, if you don't fully get anything in this video, that's totally fine. We will spend time in class practicing and relearning these things. This is sort of a preview. Last thing we're going to talk about are indicators. So indicators are chemical substances that change color in the presence of an acid or a base. And here are a list of indicators. You can see in this table the indicator is listed here, and then it tells you the color of the indicator in in an acid, the color under neutral conditions, pH is equal to 7, and the color when it's exposed to a base. There are many indicators, more than what this table shows. The ones we're going to focus on are the red and blue litmus and also phenolphthalein. So let's start with red and blue litmus. As you can see for red litmus, the red litmus paper will stay red if it's in an acid or if it's in a neutral solution, but will turn blue in the presence of a base. On the other hand, the blue litmus will turn red in the presence of an acid and stay blue in a neutral solution or in a basic solution. And you can see that here. So here we have a blue litmus paper in acidic solution, it will turn red, and a red litmus paper in a basic solution will turn blue. And so you can use these types of indicators to determine if something is acid or base. It won't necessarily tell you what the pH is, but it will tell you if your solution is acidic or basic or neutral. The last type of indicator that we're going to look at is phenolphthalein. This is something we will use in this unit. It's used in titration labs. So phenolphthalein is normally colorless, but in the presence of a base, it turns pink. And so we use this a lot of times to indicate when an acid has neutralized, or base has neutralized an acid. So this is a very popular indicator. All right, that is it for this video. We kind of just skimmed through some things about acids and bases, sort of introduce you to some terminology. We will review and learn more about these things next week. All right, have a quality day.